All right, everyone. All right, so today we're actually going to cover inductors. This is a new device, new component, kind of exciting, and I'll call this the intro to inductors. Okay, now physically, an inductor is nothing more than just a loop of wire. So that's what I've tried to draw right here, is just a loop of wire. So any wire, and you go ahead and make a coil out of it. And if you do this, you essentially have an inductor. Now, the schematic symbol is portrayed as such over here. Notice it's slightly similar to a resistor as far as the drawing, except they have these curved edges and they're trying to sort of mimic loops in the wire over here. So this is the schematic symbol that we're going to use. Now, first, let me go ahead and make a statement about resistors, and then I'm going to make a similar type of statement about inductors. Okay, now for this, I'm going to be speaking about the property. Remember that for a resistor, the property that it exhibits a lot of is resistance. So if I go ahead and say resistance R is a property that opposes the flow of current. Right? That's what we've been dealing with thus far, resistance, the property that opposes the flow of current. Well, I can go ahead and make kind of a similar statement about inductance. There's going to be a subtle difference here. So if resistance R is a property that opposes the flow of current, inductance, and now the symbol that we use for inductance, unfortunately, current has already been stolen by I. So I can't use I for inductance, and so we use L. Inductance L is a property that opposes a change in current. Okay, so think about that for a second. We know resistance, property that opposes the flow of current. Inductance is a property that opposes a change in current. Okay, so in other words, inductance gets exhibited only when the current is changing. And we're going to kind of keep that theme as we move along. But in order for an inductor, which has a lot of this property inductance, to do anything at all, it needs to have the current changing. Okay? Now I'll go ahead and do a little foreshadowing and throw something out there. An inductor just looks like a straight wire if the current is constant. Okay? So kind of going back, think about this as a wire. If the current isn't changing, this acts just like a wire with essentially zero resistance. It does nothing. As far as your circuit is concerned, this is just a wire. However, if the current changes, in other words, if it goes from 0 amps to 1 amp, that's a change in current, at which point we're going to see something that happens. Okay, now let's go ahead and kind of talk a little more. Now, the next thing that I would say about an inductor is that it stores electrical energy in the form of a magnetic field around it. So let me go ahead and let me say this, and then let me also draw this. Okay, inductors, switch colors here, go over to green. Inductors store energy in the form of a magnetic field. Okay, so let's go ahead and draw what that looks like. Okay, so I'm going to go ahead and let's draw a simple circuit here using an inductor. I'm going to give myself a constant current source just because it makes this quite a bit easier. Let's say it's got 5 amps of constant current, and let's go ahead and put this into an inductor. Now, I'm going to need to describe how much inductance this coil has, how much inductance this inductor has. Now, the unit that we use for that is the Henry. Unit of inductance is the Henry. And we'll just abbreviate that as H. That tells us how much inductance this inductor has. Now, there's ways I can change how much inductance this coil of wire has. I could add more coils to it. I can make it bigger. I can make it smaller. So I will go over those factors that affect inductance later. But for right now, let's just start off with describing how much inductance this has in terms of henries. So I'm going to make this L for inductor equal to 20 henries. Okay, so we got a 5 amp constant current source driving current through this inductor of 20 henries. Now, if we look at this from sort of a physical perspective, this inductor is really nothing more than a loop of wire. I'm going to draw it going in this direction. And let's go ahead and say that I am driving or pushing current in this direction to the left. Now, as that current goes through it, a magnetic field builds up around this inductor. And that magnetic field actually goes in this direction. Now, we're not going to get too much into the physics of how this works, nor are we going to get into the physics of magnetic fields. You don't need that to use inductors. But let's go ahead and just say we have a magnetic field and it goes in this direction. And actually, I'll draw a few more magnetic field lines. And actually, these will curve back in on themselves. Just so you can have an idea of what's happening here. So as this inductor has current flowing through it, a magnetic field develops. Now that magnetic field is storing energy, and we can actually write out how much energy is stored in this magnetic field. The formula that we'll use is E for energy is equal to inductance L in henries times the current squared divided by 2. Now, E is energy in joules. L, inductance in henries. And I is current in amps. All right, so if you wanted to solve for how much energy is stored in this magnetic field of the inductor, well, we can go ahead and just fill out this equation and solve for it. So E is equal to 20 henries. I'll include my units here, times the current squared, 5 amps squared, divided by 2. That's going to equal 250 joules. Okay, so you have 250 joules of energy stored in the magnetic field of this inductor, provided we had an inductor with 20 henries and 5 amps flowing through it. So you can think of an inductor as an energy storage device. Now, other energy storage devices that we've already used and looked at, and we've been using them this whole time as a constant voltage source, was like a battery. Now, a battery stores the energy in the chemistry inside of the battery, and then it releases it. For an inductor, however, the energy is stored in this magnetic field. So it is a bit different, the mechanism by which it stores this energy, but you do get kind of the same effect. You get the ability to store energy and the ability to release energy. Okay, so the two things thus far that we should definitely pay attention to for inductors is A, it's a storage device for energy, and B, it's a property that opposes a change in current. So let's go ahead and now start talking about this opposition to the change in current, because the energy storage that I just went over doesn't exactly describe that. It just talks about kind of what's going on, storing energy in the magnetic field. So let's go ahead and talk about opposing a change in current. There we are. Now, we do have two situations that could occur. So if I go ahead and take another simple circuit using an inductor, I'll take a constant voltage source, and I'm going to set up this situation over here. Now, I'm creating a little selector switch over here. And let's write A and B. Some voltage source and some inductor. Now, if you notice, when I go ahead and take the switch and flip it over to A, I get current flowing into this inductor. Now, provided that I had no magnetic field already in this inductor, in other words, I have zero current flowing through it, and then I flip the switch over to A, I start to get current flowing into it. So I'm going from 0 to something, to some amount of current. That's a change in current. Now, when we have that change in current, and once we start getting current flowing into the inductor, into the device, we're going to start building up a magnetic field around this inductor. I'm going to call that an expanding magnetic field. And I'm going to label this as A. This is what happens when we flip the switch over to A. We get an expanding magnetic field. Okay, so I'm going to go ahead and draw my inductor here. We have current flowing through it in this direction. And I'm going to simplify the way that I draw these magnetic field lines. And I'm going to say that they are moving outward. They're expanding. They're getting larger. We had zero current going through the inductor. Now we have some current going through the inductor. And so this magnetic field is growing. We have an expanding magnetic field. Now this happens whenever current is increasing. Okay, so that's what happens when current is increasing. Now, once we have a magnetic field in there, let's go ahead and take this switch, flip it over to B. When I flip this switch over to B, remember, I had a magnetic field built up around this inductor. I have energy stored inside of the inductor, and now I'm going to flip it over to B. Well, what did I do? I just took this energy source and I now gave it a path for that energy to dissipate. It's going through this resistor, right? So if I go ahead and let's draw this now in green, I take my switch and move it in that direction and now make this connection. I've disconnected it from A. Now I've reconnected it to B. I've now given a path for current to go through this resistor and for the magnetic field to collapse. So when we move it to B, we get a collapsing magnetic field. So let me go ahead and draw another inductor, and let's say I is decreasing, and now our magnetic field is collapsing. So I'm drawing my arrows going inward. The magnetic field is falling. We're taking energy away from this inductor and we're putting it through this resistor. So whenever current is increasing, we have an expanding magnetic field, and whenever current is decreasing, we have a collapsing magnetic field. Now, I went ahead and set that up because this expanding or collapsing magnetic field, in other words, this changing magnetic field, creates a very interesting situation. As the magnetic field increases, and only during this change, an EMF, and remember, EMF is electromotive force. also known as a voltage, is produced in the opposite direction. Okay, this is subtle, so please pay attention here. As the magnetic field increases, and only during this change, an EMF, a voltage, is produced in the opposite direction. Okay, so here's what's going on. We had zero magnetic field, we put current through it, and we have this expanding magnetic field. As the magnetic field expands, it moves through the coils of this inductor and produces a voltage. I'll say that again. As the magnetic field expands, it moves through the coils of the inductor and produces a voltage. So just by virtue of putting current through this guy starts acting like a battery. Let me go ahead and draw that out. Okay, so going back to this drawing over here. Actually, let me go ahead and draw another one. This time I'll make it a little simpler. I'm just going to put a switch in here. Okay, when I have the switch open, I have 0 amps flowing through here. Once I close the switch, I now have some amps going through here. I'll just say current is greater than 0 amps. And so that produces this expanding magnetic field. As the magnetic field expands, it moves through its own coils of wire and produces a voltage opposite of the change that created it in the first place. So in other words, this circuit when I close the switch actually creates a voltage. The inductor creates a voltage in the opposite direction. Temporarily. So this inductor is creating its own EMF in the opposite direction. Well, what that ends up doing is it opposes the instantaneous change in current. So let's go ahead, let's graph this out and kind of see what happens here. Now I'm going to go ahead and plot voltage along the Y. Along the X, we'll just say time. So while the switch is open, we have 0 volts applied to that inductor, right? It's open. We have no current flowing through it, so volts across this inductor is 0. Now, when I flip that switch, the voltage will go up to some value. So let's go ahead and say right here, switch is closed. Well, remember that as soon as we have a change in voltage, we're going to have a change in current. When we have that change in current, we get an expanding magnetic field. As we get an expanding magnetic field, an EMF, another voltage, is created that is opposite the direction that originally created it. So we actually get this temporary backwards battery. Temporary backwards battery. This temporary backwards battery is opposite of our voltage that created the initial change, right? Look at the direction over here. We're trying to push current in this direction, but the voltage created in the inductor is pushing in the opposite direction. So I've shown that by having this line go downwards. But remember that this temporary backwards battery is only formed when I is increasing. At some point, I no longer increases in this circuit, right? Because once I've thrown the switch over here, I have, after some period of time, I have no more changing current. So I don't have an expanding magnetic field anymore. There's no decreasing magnetic field. It's just the magnetic field is as big as it's going to get. So at some point, there's no more changing magnetic field. And for that reason, this voltage isn't produced indefinitely. That's why I said it's temporary. And so this backwards voltage tapers off. Now, we have a name for this. We call this a back EMF. Now, there's a few other names for it, and I'm going to list them all out because why not? Different people say it different ways. You're going to see the term counter EMF. You may see CEMF for counter EMF, right? Because it's a counter voltage. It's a counter electromotive force. It's countering the initial guy that caused it to change in the first place. So counter EMF, CMF, or back EMF. They're all the same thing. Counter EMF is equal to CMF, which is equal to back EMF. They're all the same thing. Just three different words for saying the same thing. Now, what I haven't plotted on here yet is current. What does that mean in regards to the current? Well, if I'm applying a voltage source causing current to flow in this direction, but I have in response a back EMF that's opposing this current flow in the first place, I'm not allowing the current to change instantly. In other words, it's going to take some time. Remember that the back EMF doesn't stay at its max value indefinitely. It goes to some value, and then the change is no longer occurring, so the back EMF peters off. And so the current ends up looking like this. Let me draw this on another sheet. The current wanted to do this. At some point, the switch is thrown. The current wanted to change instantly. However, the inductor is not allowing that to happen. Just like before, we said it's acting as a temporary backwards battery. So it prevents the instantaneous change in current. The current should have done this, but that temporary backwards battery doesn't allow it to happen. So the current actually ends up looking like that blue line right there. This is why I made that previous statement. Inductance is a property that opposes a change in current, because it's only during this change in current that we see anything happening, that we see the non-instantaneous rise of current. Now, this process is called self-inductance. Self-inductance, I'll go ahead and define as the action of generating a back EMF which opposes the original change that produced it. I'll say the original change in current which caused it. Okay, so I know it's a little wordy, but think about this for a second. The word inductance is to induce something, right? Inductors, inductance, inducing a voltage. It's inducing a voltage in itself. It's self-inducing a voltage. It's self-inductance. That's kind of where this thought process is coming from. Right? We have a change that causes an expanding magnetic field, which creates a temporary backwards battery, aka back EMF. That back EMF opposes the original attempted flow of current and doesn't allow it to instantaneously rise. That whole sequence of events, that whole story, is self-inductance. Okay? Now, let's go ahead and flip the switch in the other direction. Now, I moved it from A to B now. And previously at A, let's say we already had as big of a magnetic field as we possibly could have had. Well, once we move it to B, we're going to get a collapsing magnetic field. Now, again, we have a collapsing magnetic field. That collapsing magnetic field is going to, again, create a temporary battery that induces a voltage that gets applied to this resistor. So we can go ahead and graph this out yet again. Now our current's going down. So let's go ahead and say this was when the switch was thrown from nothing to A, occurred here. And then now we flipped it over to B over here. Now before, when we had the expanding magnetic field, a voltage was induced in this direction. Which caused the current to slowly increase. However, now that we have a collapsing magnetic field, because we flipped the switch over to the B position, we get yet again that same exact back EMF, except it's created in the positive direction. Again, that change is only temporary because this magnetic field cannot collapse indefinitely or infinitely. It reaches a point where there's no more magnetic field. You've taken all of the energy out of the device. You've siphoned off all of that energy that you had stored in this magnetic field. So at some point we have no more magnetic field, but this back EMF was still generated. Well, what does that mean for the current? Well, the current flowing through the resistor does not change instantly from some value to 0. It has to take some time, and it takes the amount of time that it takes for this back EMF to dissipate. So when you go ahead and look at only the current, I'll put a dotted line for our switch. Current is at 0. Switch gets thrown, expanding magnetic field, back EMF generated, current rises slowly. Switch gets thrown over to B, back EMF generated in the positive direction, and keeps the current from falling instantly. I think that's a good way to view and look at this device. Okay, so I'm going to keep this part of the lecture to theory. We will work and calculate with this next time, but there's a few other things that we should talk about in regards to inductors before we continue on. Okay, we need to go ahead and quantify this inductance. Well, what changes, what affects the amount of inductance that an inductor has? Factors that determine inductance. Well, first off, let's take our real simple inductor here. Nothing more than a coil of wire, just to have a point of reference. Well, first off, number of turns. Each loop of that wire is a turn. Number of turns. If I have more loops of wire, I can have more magnetic field, which means I have more inductance. So I'll just go ahead and say more turns equals more inductance. Okay, next factor that can affect the amount of inductance an inductor exhibits: the cross-sectional area of each one of these coils, of each one of these turns. Cross-sectional area of the coil. I'll go ahead and just say if you double, it's the square of the coil diameter. No, let me write that. Square of the coil diameter. So if you double the area the amount of inductance doubles. Okay? So each one of these coils from the side looks kind of like this. So if you double the amount of area, you double the amount of inductance. Okay, so you can add more turns, you can subtract more turns, you can increase, decrease the cross-sectional area to change inductance. Also, the length of the coil. So if I make this longer, spread it out, stretch it out, I don't have them as tightly packed. And if I don't have them as tightly packed, I have less of an ability to concentrate the magnetic field lines. So the longer the coil is, without changing any other factor about it, I haven't added more turns, all I'm doing is taking it and stretching it out, I will get less inductance because I have less of an ability to concentrate those magnetic field lines. The longer the coil, without changing anything else, the less inductance I get. I'll just leave that at there. Okay. So number of turns, cross-sectional area, length of the coil. And the last one is the relative permeability of the core. Sounds like it came straight out of some sci-fi movie. The relative permeability of the core. We call that mu R. Okay, up until now, I've said that inductor is just simply a coil of wire. And that's true. If I take some coil of wire, I have an inductor. However, when I do that, I have air in the center of this coil. Well, let me go ahead and say that. This is an air core inductor. Air only has so much capacity for a magnetic field. But I can put other things in the center of this coil that are much better at holding a magnetic field. Especially things like ferrous metals, right? Things that can magnetize easily. A chunk of iron will do it. Okay, so I have different things that I can put on the inside. Cores. I can have air, I can have iron, I can have powdered iron. What else? What else? There's a material called ferrite that gets used. Those are actually the only ones that are coming to mind right now. I'm still thinking. Yeah, I don't think I've ever used any other type of inductor. It's either got air, iron, powdered iron, or ferrite, which is essentially the same thing. Okay, now associated with each one of those different cores is some ability to concentrate magnetic fields. Now, with this means air to iron. Iron has more of an ability to concentrate magnetic field lines, so iron has a higher mu sub r. Air has a greater mu sub r. So I can go ahead and say the greater the mu sub r, the more inductance I get. Okay, because I have more of an ability to concentrate magnetic fields with something like iron than I do with air. Okay, now with this comes a few different types of inductor schematic symbols. Let's go ahead and cover those. Now, on a schematic, you're going to see a couple of different representations for inductors. And truthfully, they kind of don't matter because at the end of the day, all you care about is the number of henries that an inductor has. But for completeness, let's say I got an air core inductor. It's just the inductance schematic symbol. But let's say instead of having air in the center of that coil, I shove a chunk of iron. I now have something called an iron core inductor. And they represent it with two solid lines above the inductor. This just tells the person reading the schematic, hey, I don't have air in the center of my inductor. I actually have an iron core. Now again, this just really kind of doesn't matter because once I say that L is equal to 10 of an air core, and I say that L is equal to 10 for an iron core, it's essentially the same inductor anyways. But the air core inductor is going to have to physically be larger in order to concentrate the same amount of magnetic field that an iron core inductor would. Okay, another type of inductor you're going to see is the powdered iron or ferrite core. Same thing, the inductor symbol, except instead of 2 solid lines, you're going to get 2 dashed lines. Now, when you're talking about powdered iron or ferrite, quite literally what they do is they grind up iron, they turn it into filings, and then they put it into some glue and they mold it. And they call that ferrite or powdered iron. Now, if you think about an iron core as being solid, and if you think about grinding up those 2 lines and turning them into dashed lines, that's where you get your powdered iron from. Okay, and the list continues. We could also have a variable inductor. Now, anytime you want to make a component variable, at least for the sake of drawing it on a schematic, just put a diagonal line through it. This just means that we have an adjustment. We have an ability to change it. This is a variable inductor. Now, physically, what does that kind of look like? Well, if you've ever opened up some really old electronics, especially something like a radio from, see, I just feel like the 80s isn't that long ago, but it kind of was. The 80s was already 30 years ago. All right, so if you open up a not so old radio from the 80s, which is actually kind of an old radio, you may see a tin can, shiny, metallic, silvery, with something like a colored screw on the top of it. And if you look at the bottom, you're going to see 2 wires coming out of the guy. And if you take this tin can apart, what you're going to find inside of it is a coil and they have created a core that is threaded that's my screw. And if you turn the threads, if you turn this righty-tighty, lefty-loosey, if you turn it right, or clockwise, I guess, then it's going to go deeper into the coil. That's going to increase your inductance because you're putting more of a core inside of it. Down here, you just have air inside of the coil. But if I turn the screw clockwise and drive it deeper inside of that coil, I will get more inductance. And similarly, if I go counterclockwise, or if you're in Europe, it's anti-clockwise. If you go anti-clockwise, you actually back the screw out of the coil, putting more air in between or inside of the cross-sectional area of that coil. So you're decreasing the inductance. So that's one way to make a variable inductor, and this is what used to be done for radio electronics, all in electronics really, since, the 20s and 30s all the way to, you don't see these as much anymore, but sometimes you need to tune the circuit, and so you want to change the inductance ever so slightly inside of your circuit, and so they'll do this so that you can adjust it. And then usually they put like a drop of glue on top of it so that it stays set in that setting for the rest of its existence. Okay, enough about variable inductors. Let's talk about another variable inductor. This one is the tapped inductor. Don't know why I switched to blue. I just did. Now with a tapped inductor, it's got more than just two wires. So they'll put a wire over here, put a wire over here, and maybe another one over here. And depending on which two, maybe I go between here and here, I get less coils, so I get less inductance. In the middle, I get more coils, hence more inductance. And over here and here, I can increase the amount of inductance by simply switching or clipping onto one of these other coils. And so they make inductors like this. If you go online and actually Google tapped inductors, this is used a lot for like microwave radio circuits and some more advanced circuits like that. And they'll actually have like a giant coil with taps coming out of it. So this is another type of inductor. If you think about your loops of wire, your taps would get, connected here, and so forth. Okay, so those are our different types of inductors. Again, from a practical point of view, a Henry is a Henry. Okay, let's talk about what inductors do in series and in parallel. Running out of paper here. All right, let's go with inductors in series. So I'm going to take a couple of inductors and I'm just going to Oh, let's make this fun. Let's make them iron core. I don't know how that makes it more fun, but it just is. Okay, let's say that L1 is equal to 10 henries and L2 is equal to 10 henries. Well, inductors in series, much like resistance in series, or I should say inductance, I should speak in terms of the property. Inductance in series does the same thing that resistance in series does. It just adds. LT is equal to L1 plus L2 plus ... plus Ln. So in this case, I can replace these two inductors with one inductance where LT is equal to 10 plus 10 henries, or 20 henries in this case. And that takes care of what inductors in series do. Inductance in parallel inductance in parallel, if it adds in series, and you're not shocked by this, you're not going to be shocked by this next part. One over the inverse of the summation of the inductances inverted. Or for two L's, LT is equal to L1 times L2 divided by L1 plus L2. It does the same thing that resistors in parallel do. I'll make these air core inductors. Let's say one of them's 10 henries and the other one's 5 henries. Well, I can create an equivalent inductance for both of these in parallel, and it's just LT is equal to 5 times 10 henries divided by 5 henries plus 10 henries equals 3.33 repeating henries. Okay, so we've gone over theoretically how inductors work, the whole concept of self-inductance, how it opposes a change in current, and I don't think this is a very intuitive process, the whole idea of self-inductance. So I do strongly suggest watch this lecture again. I'm also going to link to another one. There's another person who also discusses this that I think does a pretty good job as well. So I'm going to throw that out there as a resource as well. And we're going to pick up on how to calculate this curve and all of that fun stuff. We're going to pick that up next time, all right? Okay, thank you. I will see you guys later.